Geology. Mini Geology. This is the Mini Geology radio show here from KPFT HD2 channel in Houston, Texas. Hello to the nation, hello to the world, and maybe some of you astronauts there in the International Space Station, you're listening to us because we know we are reaching you through our radio waves and the brotherhood we have with NASA. Hello to everybody. Today we are going to talk about geothermal energy. Geothermal. Well, to talk about geothermal energy, today we have here in the house Malcolm Ross. Malcolm is an adjunct professor at Rice University in the Department of Earth, Environmental and Planetary Sciences. Welcome, Malcolm, to the studios of KPFT Houston.
Thank you, Daniel. Thank you for having me. I look forward to our conversation.
All right. So, Malcolm, you didn't have voice for 2 seconds, but here we are back on track. Thank you very much for coming here and talk about the geothermal energy, the source of energy that we don't listen to as often as I would like, because we have a lot of debates today, including the conventional sources of energy and the renewables. But within the renewables, and geothermal energy should be into the renewables, is not so acclaimed as the other ones. Let's start from the basic. The geothermal energy, which is, as the word says, is heat stored in the earth crust and that we can transform into energy. So, Malcolm, the very basic question is, why is the earth hot? Where is the heat coming from?
So there's really two fundamental sources of energy in the universe. One basically is fission, and the other is fusion. And you think of the sun as fusion, and we're using the sun in many different ways to power solar panels and actually create the oil in the ground. All those things are essentially fusion projects. Fission is nuclear. You think of a nuclear power plant. That's a fission plant. But in the center of the Earth, you can think of a fission power plant as well, where there are radioactive materials in the crust that are decaying and releasing heat as a part of that decay process. And that heat is stored in the Earth, and it's actually kept it very hot to a point where the core of the Earth, the core is liquid from all of that heat. So there's a vast reservoir of heat in the Earth, and some of which is flowing to the surface, and in varying degrees of very hot to not so hot, and that's what we're tapping into. So it's really fission that we're tapping into.
And when we talk about heat, which kind of temperatures are we talking about?
The hotter the better when it comes to geothermal, really. But the classical geothermal, it has to do with steam. So you're talking about, above 100 degrees C so that you can get that steam. But really it's above 200 is considered a good resource. But some of the latest technology that I'll talk about is looking to up to 350, 400, or 450 degrees C.
All right. So what are the simple elemental components of, if I can call a geothermal system, from which we extract the heat to produce the electricity?
Yeah, so a geothermal system involves some penetration of the earth to tap into that reservoir. And that there's various forms of that. We'll talk about that in a minute. But once you produce that fluid or that steam at the surface, you've got to convert it. So you have to have some kind of surface power plant. Very often that includes turbines, where you're spinning a turbine. Just like you could think of a waterfall, a dam and a waterfall spinning a turbine, it's the same principle. Then there's also, you have to deal with that material once it's come out of the turbine. And so there's various recovery systems that are involved as well.
And can we produce geothermal energy everywhere in the world, or there are specific areas where we need to go?
Right. So that depends a little bit about the technology. The earliest forms of the technology really dealt with places where there was hot water bubbling at the surface. You know, think of Iceland, think of Yellowstone. Actually, the very first geothermal power plant ever in the world was in Italy. You're probably proud of that. It's all of these places are where it's very hot at the surface, and the water is boiling at the surface. You think of the geysers and places like that. So that's the first generation. The next generation began to realize that those places are very limited. You know, you think you go around the world, there's not very many places you can go see water boiling at the surface. So the next generation of geothermal began to go to the subsurface and essentially try and produce that boiling water in the subsurface. This is called enhanced geothermal.
But in the subsurface, we don't have boiling water.
Right, so they introduce water. So you take hot rock, you fracture that hot rock, you pump water through it, and it comes boiling to the surface, and essentially you've recreated in a man-made way what was once the natural way.
I see. So we need a system in which we have a dry, hot rock that is fractured, and then we introduce the water. The water, it becomes hot because the dry rock is hot, and then we recover that water.
Exactly, yes. And so often we drill down into rock that's not fractured. In fact, that's the preferred way, because then you can fracture it in just the way you want it, just between your injector well and your producer well, and not have to worry about water loss. But if you drill into rocks that are already fractured, you may not have the wells in the right places because the fractures are in a different direction than you thought, but it also leads to leakage. So one of the big challenges with geothermal is the loss of water in unexpected fracture systems. And it has to be dry, because if you drilled into a wet system, then you're mixing your water with the water that's in the subsurface, which is often a brine or salty, or it has all sorts of materials in it that you don't want to produce at the surface. So that's why you're looking for the dry component of this. Otherwise, you're mixing.
So, and are there specific areas in the world where the rock is hot and dry? Or they are randomly around the crust?
No, there is very specific regions around the world where it's hot. The dry, that's a little more random, because it has to do with the aquifer and, you know, where it rains and where it's not raining, those kinds of things. But in particular, it's where there's subduction zones. So everyone classically thinks of the Pacific Ocean subducting basically almost entirely around its edges. So we call that the Ring of Fire. So you start down in South America, you go all the way up there, pass through Mexico, through the west coast of the U.S., around Alaska, down Japan, all the Philippines, all of those areas around the Pacific is classic good geothermal country. And then the geology depends on whether it's dry or not. Now, some of the newer technologies get away from that. So that's one of the limiting factors.
Wait a second, before moving into the new technologies. So it's just around the Ring of Fire, or there are other places like plate boundaries in general?
Yes, plate boundaries in general. East African rifts, for example. Kenya has geothermal. A lot of the sort of countries along the East African region. The boundary in Italy where they started producing was the subduction related to Africa going underneath Europe, for example. So almost anywhere you have the plate boundaries with excess heat is where you're going to find good opportunity for geothermal.
And when you talk about drilling a well for injecting the water and then drilling another well to produce the hot water, you are thinking about which depths underneath the ground?
Well, the depth is controlled by what we would think of as the geothermal gradient. So the hotter it is, the more quickly it gets hot, the shallower you have to drill. And so they vary around the Earth. In some places it's less than a kilometer down. In other places, you have to go to 3 to 4 to 5 kilometers to get to a place where it's hot enough.
So we could say that is analog to the drilling experience in the oil and gas industry.
It is, very much so. But the challenge is that it's hot. So we're used to drilling actually in the cooler parts of the earth, because if it's hot, we burn out our petroleum and we wouldn't have any petroleum to find. So a lot of the technology and thinking around drilling in the oil and gas world relates to cooler drilling. When you get into the hot drilling, especially hot, dry rocks, and what we're really talking about there is granites usually, when they're that hot, they are extremely difficult to drill. They end up melting the drill bit. You can just imagine how often you have to trip and bring the dull bit back to the surface, put a new bit on it, start working some more.
So same depth, but completely different challenges.
Yes.
And so now go ahead with what you were talking about, the technologies of how to extract the heat from the rock and produce energy.
Right. So the earliest stuff we talked about is at the natural springs at the surface, the Yellowstones and so on. The next generation was this injector-producer geometry called enhanced geothermal. But now what we're finding is that there are some serious challenges with the enhanced geothermal, and we're looking for the next generation of technology. The challenges involve things like this fracturing, right? Fracking is a bad word in a lot of places that will limit your ability to do a particular activity. There's also induced seismicity. In fact, the largest earthquake recorded in Korea was recorded just recently, and it has been proven to be associated with geothermal. There's also at least one production plant in Switzerland, a geothermal plant, that had to get shut down because it was inducing seismicity. So there's several challenges. There's also the problem of taking clean water from the surface that we could be drinking, we could be using in agriculture, pumping it into the rocks, having it dissolve rocks and salts and heavy metals and radioactive minerals and all that in the subsurface that's present in the granite, and then you bring it to the surface and you've polluted that water, essentially. And then you have to clean it up, and what are you going to do with the pollutants that you just brought to the surface? So there's some serious challenges with this enhanced geothermal concept. So now we're moving to advanced, or the next generation. And
when did it happen, this shift?
It's happening now. I just went to a conference last year, and this was the first time in October people were openly saying that enhanced geothermal is not working, and that the investment dollars that people are willing to invest in projects is going down because they're feeling that it's a challenge.
Let's call it phase one, and we're moving into phase two. And just for the sake of simplicity, because the phase one, you call it enhance.
Well, phase one was really the original sort of producing where it was auto.
Okay, so there are three phases.
Yes, I would say so.
We have the classic geothermal, which is the phase one.
Yep.
Then move into the enhanced geothermal system, phase two. And this transition, when did it happen? With the modernization of the civilization, maybe century ago?
The very first surface geothermal was about 1903 in Italy. The very first enhanced geothermal started in the 1950s and 60s.
Okay.
And
then phase three?
Phase three has not started yet.
All right. So, but you said that we're moving into phase three, but you already highlighted a lot of problems with the geothermal energy related to the environment. And I'm going to just try to list them as you said that I capture that you have areas that they are dry and we need water in those ones, so it's not going to be accepted very well by the locals of the society. Then you said that we need to frack, and frack can incite resistance. You said that there are man-made earthquakes, which we already know through the oil and gas industry. And then you said that you bring up, together with the heat and the energy, you bring up like waste.
Yes.
So how comes that we have in mind geothermal as being a clean and environmental friendly energy with all of these challenges?
So if you look at the trends in geothermal, they've flattened. So in 2010, The total amount of installed geothermal power was about 11,000 megawatts. In 2015, it was only just over 12. So in 5 years, they added basically only 1,000 megawatts. And that has to do with the fact that this investment is going down. People are struggling with all those environmental problems. So the question is, what does phase 3 look like? And that's being found out now. That's the focus of some of my work. I believe that the system that is going to be most successful is what we call a closed loop. So you erase all the problems related to dissolving material because you're closed from the rock. You have no induced seismicity because you're away from the rock. Many of those things you listed are eliminated by just closing the system off from the country rock.
Explain us what is a closed system.
You could think of it as a U, kind of a U-shaped thing where you go down, you go horizontal in the hot rock, and then you come back to the surface. So you still have the injector and producer concept, except now the injector are produced, connected by a physical pipe. And then back at the surface, you produce the heat, you use the heat, you do the things you would do to produce the power, then you bring that working fluid and back to the injector and you re-inject it.
And so the medium that you use is which sort of liquid is it? The one that you set
Right.
down?
So the classic one is water, but it has some thermodynamic characteristics that don't really make it particularly good compared to what we think is going to be the best is supercritical CO2. So you actually take CO2 out of the atmosphere and use it as your working fluid in the subsurface.
What does it mean, supercritical?
Supercritical is a state of matter. You know, you think of gas, liquid, and solid as being the three states of matter. In fact, there's a fourth state. It's the supercritical state, which it acts sometimes like a liquid and sometimes like a solid. So you think of like dry ice, for example. That's a supercritical state. This is a state of where the CO2 behaves like a liquid and like a gas.
I need to call my professors and tell them that they have to teach me this fourth state of the material.
Yeah.
The supercritical part. And do you say that it could be CO2 because of the availability of CO2?
It's actually because of the thermodynamic characteristics of that particular matter has characteristics for heat capacity, for extracting heat from the reservoir and carrying it in a high volume, much more than water can, and it has to do with the chemical bonds and all that kind of stuff.
Okay, so you insert CO2 in supercritical CO2. Mm-hmm. It goes down relatively cold and comes up heated, so hot and pressurized, I imagine.
And pressurized, right? And hot and in close to or in a gas state. And that's the other important characteristic. It's not only the heat capacity, but also the expansion, right? When you think about going from a solid to a gas or a liquid to a gas, one of the big things that happens is expansion. So you can use that expansion also to generate electricity. So not only do all the normal things you would with heat, but you can also maybe produce double the amount of power just by using the expansion. So the other interesting thing that happens is on the downgoing side, where the supercritical stuff is relatively cold and dense, it's heavy. So it goes down. Gravity pulls it down. And then as it gets heated up, it expands and the density goes down. So the upgoing part is much lighter. And so it turns out that it circulates without pumps because the heavy side is pushing down and the light side is going up. And that's super important because you don't have to have an extra electricity burden to pump this fluid. It just flows by itself. But you still do have to get it from hot and gaseous back to supercritical. So there is still a penalty you have to pay to convert that back to supercritical state in order to make it a closed loop. But it's less than you would normally pay for all the other things you have to do if the working fluid was water. You could also think of like a refrigerant, the stuff that's circulating in your refrigerator. Might also be a very good working fluid. Methanol might be a good working fluid. There's a whole series of different fluids that we might be able to use because it's closed that we would never use in an open system, because you don't want to pump that stuff into the rock and pollute the country rock and do all that kind of stuff. You'd never get permission to pump some of that stuff underground and have it leak.
Well, no, maybe in Texas.
Maybe in Texas.
By the way, do we have geothermal in Texas?
Good question. So there are different places. If you go deep now and you go with a closed loop, you can get away from the ring of fire. You can start getting into a much broader area, which makes the economics look much better. But there are some places in the world where there's such a large stack of mud that you have to get through in order to get down to that hot granite that it's less beneficial. And of course, East Texas is a classic example of that. So is, by the way, places like Holland, where you have these huge, wide, essentially mud pits that are going to be expensive to drill through. So there's still going to be places that are less advantageous, but there's going to be vast, larger areas that are going to be attractive for geothermal if it's closed loop and if you go deep.
So tell us again, if it is closed loop, why we can all of a sudden expand our area of interest outside of the plate boundaries?
Because the whole trick is to get hot more quickly. And if you can get to areas where it's hot and it's deeper, then you can start using areas that are where the geothermal gradient is not quite so steep.
But in that case, you have to drill deeper.
You have to drill deeper. That's right.
Okay.
One of the interesting aspects of this is the movement in the geothermal world to reuse oil and gas infrastructure. So you have a well, it's already 10,000, 20, 30,000 feet deep. Why not start there? Now, it's not going to be hot enough, because if it was hot enough, you wouldn't have hydrocarbons there. But that's maybe 90% of the drilling that needs to be done. Maybe you just need to go a little deeper and pay only the extra 10% to get to deep enough than you would otherwise have to drill all the way from the surface.
So you are proposing that geothermal piggyback on the oil and gas industry?
Yes. In fact, the province of Alberta in Canada is making it very financially advantageous to companies to do exactly that. And there's a big oil and gas industry up there, so there's a big push to do that. And the geothermal gradients in that part of the world are higher. Turns out one of the coldest geothermal gradients in the world that I'm aware of in the oil and gas is West Texas. The Permian Basin of West Texas, which is hugely prolific, is also pretty cold. So Texas turns out to be not very attractive from the geothermal world. But I think my opinion about this whole renewable energy thing is you can't pick one winner. There's always going to be one that's going to be better than another. And in some places, geothermal is not just going to be as good as wind and solar, for example. But let's play them all. Let's not just make our bet on two, wind and solar, that have their own set of problems. Let's go where whatever's best in whatever place. So New York State, for example, might be a very attractive place for geothermal, but you're not going to have a good chance with solar panels, for example, and wind. Who
is looking seriously and dynamically to this phase 3? When I ask who, I mean which kind of industry and which countries they are moving into this phase 3.
To my knowledge, the only place where this is happening is in the United States, and in particular in California. California is actually a plate boundary, so they do have some classic geothermal. They were some of the earliest geothermal in the United States in the area called the Geysers of California, around the Coso Valley. But there is a project running right now to convert a enhanced geothermal well to a closed loop well. And what they're going to do is take an existing single well and put a thin tube, an insulated tube inside of it. So instead of having a U where you have an injector and a producer that are separate, you're going to have the injector and the producer in one place.
I see. It's like a straw inside another straw.
Straw and straw. That's what we call it. Exactly.
Uh-huh.
Yes. Now, that's a thermodynamically challenging because, you're taking cold stuff and putting it down the outside, and then you're trying to bring the hot stuff up the middle, but the cold stuff on the outside is making the hot stuff in the middle get cold. So, you'd rather separate the two if you can, but where you already have existing infrastructure, like in geothermal fields or in oil and gas fields, it may make more sense to put straw and straw.
So I see that there are a lot of ideas, and the engineers are probably trying to apply them. But why don't we see them already in the market? Why don't we have energy derived from the geothermal? Why don't we have geothermal energy available where we can buy it, where it becomes competitive against the other sources?
In some places in the world, it already is. Iceland, for example, produces an abundance, actually an overabundance of electricity from geothermal. The Philippines also is very strong in that area, for example. But as a broad acceptance, it is challenged currently relative to wind and solar, particularly because it involves things like drilling wells. And the drilling, as I described before, is very expensive because I talked about the melting of the bit and all that kind of thing. The upfront expense of a geothermal project is too high for a lot of investors. And so right now we are struggling when competing with solar panels where you just put panels up, right? It's not a big upfront investment. So that's been the biggest challenge. So the bringing the cost of drilling down is the single most important thing to cutting loose geothermal.
Do you mean that in Iceland and Philippines they are doing it even if it's not economically convenient?
It is convenient for them because the heat flow is so high that they only have to drill a very short distance and it's already hot enough. And so the cost of drilling is low because they're only drilling a short distance.
I see. I would like to see more, we have these images of the wind farms in the North European countries, but we don't have the images of what is a geothermal power plant, and we don't know that the Philippines, they produce, I think, maybe 1/3 of their energy from the geothermal. Maybe also Iceland, they have 30% of production of their electricity derived from geothermal.
Right. Interesting because, in the places where it's working, it's doing this enhanced technique, and so you have a lot of steam going to the surface, and you have steam releases and so on. So that's one vision. But if you go with this closed loop thing, you would never see any of that. What it looks like is essentially what you think of a nuclear power plant and the footprint of a nuclear power plant. We could produce the same amount of electricity that the nuclear plant does in its footprint. In that same footprint, we could produce the same amount of energy, but geothermally. So it's a very high density thing. If you wanted to do that with wind or solar panels, you'd take thousands of acres of space because the density of the energy is so much lower. The sunlight hitting the earth or the wind power that you can generate, you just need vastly more space. So one of the nice things about geothermal in general and the closed loop in particular is the density, the conservation of space. One of the interesting projects that's happening at Southern Methodist University right now is looking at actually taking over coal-fired plants, existing coal-fired plants that are going to be retired, and converting them into geothermal plants and drilling on the site. And that's an interesting option because all the rest of the infrastructure is there. The wires for the transmission are there. The environmental impact has already happened, right? So that's a very interesting idea, I think, that's being researched is where are the best coal-fired plants that you could take out of service and replace with a geothermal plant on the same footprint where the community's already invested and all that kind of stuff.
So who is advocating for the geothermal energy? Is there, are there lobbies, especially if you say that this phase 3 is present only in the United States? Who is advocating for it? Are there, which kind of private industries? And are there activists that they express their support for geothermal like we all know that they are for wind and solar?
I don't think there's I have not seen that kind of activism and support for it. I think there There are some relatively large, I mean, right now, geothermal, it doesn't have the momentum. They don't have the excess cash flow to invest in lobbying and so on. If it was more successful, I think you'd probably see more lobbying for it. And I think that this phase 3, this next generation, maybe we'll see more of that. It's a little bit of a chicken and the egg thing. But one of the biggest advocates for power, at least in the United States, is the U.S. Department of Energy. They are a big supporter. They have an Office of Geothermal Studies, and they do a great deal of funding of research in geothermal. So they're about to fund something called Forge, which is going to be a geothermal test site that is going to do all sorts of experiments in geothermal, and they're down to choosing 2 sites. So very shortly, there's going to be a big announcement about a Center for Geothermal Research funded by Department of Energy, because the Department of Energy recognizes the value of that as a resource.
Is this going to be a university or a research institute?
Yes, it's paired with universities. For example, the one that I know about is paired with the University of Utah, and it's at a geothermal site in Utah in the U.S. Basin and Range, which is also a very hot region. I think the other one is paired with California universities, I believe. So yeah, they're affiliated with national laboratories and universities.
So who has the know-how on the geothermal energy today in the worldwide? Where are the wise men and women that know about geothermal?
I guess I would have to say the biggest company in the game is a company called Ormat. And Ormat is actually an Israeli company. And they're consuming a lot of other companies. They're growing. They're the go-to people for the surface plant, mostly around the generation capacity. The drillers are their own group. But for example, Baker Hughes had a big geothermal drilling department. One of the interesting things about drilling costs is it's tied to the oil and gas drilling cost, because as the oil and gas drilling picks up and there's more and more rigs active, then the number of geothermal rigs goes down because the price is going up, supply and demand. Right now, it's actually not that expensive to drill a geothermal well because, well, at least we're recovering in the oil and gas patch now. But for a long time, in the last few years, it was relatively cheaper to drill geothermal. But it's an interesting sort of counter correlation with oil and gas.
You said a company from Israel. Is that
Yeah.
because they have geothermal energy there?
They are also plate boundary, near plate boundary, but I think it was more around the innovation related to the power production. Research was done there. I'm not aware of a lot of geothermal in Israel. They are using organic Rankine cycle, for those people who would know what that is. But they were the first ones to use that.
I see. And what about the academia? Where are the professors that they study geothermal? Where are the universities that they teach geothermal?
One of the biggest ones is Southern Methodist University in Dallas. They have a very large program there, a good program with a lot of good people working. MIT has some folks. I was just looking at a university.
Well, we should say Italy then.
Yeah, there you go.
Maybe the Lardarello since 1903.
Oh, yeah, Cornell University. That's who I was just trying to remember. Cornell University has it. University of Utah in relationship to this Forge site. But it's just like you were saying at the very beginning, how geothermal is underappreciated. I think it's underappreciated by the geoscientists and the teaching of it as well. So if you go to most schools, like Rice University where I work, it's not even mentioned in the curriculum.
What do I need to study if I want to enter this world of geothermal energy? What are the subjects and the disciplines that I need to master?
I would say they're not that different from the oil and gas industry, and I think that's why Houston is uniquely positioned to become a power player in the geothermal space, is because of the vast majority of experienced geoscientists, reservoir engineers, project managers, people who are used to working with high pressures and temperatures, explorationists who know how to look for subsurface geology. These are all sort of basic skills that you would use in oil and gas, but also would help you in the geothermal world. What you're looking for is different, right? In oil and gas, you're looking for sedimentary basins and all that kind of stuff. But in geothermal, you're looking for granitic material and all that. But, in oil and gas, you'd avoid granite when you found it. But in the geothermal world, you'd go look for it and avoid the sedimentary deposits because they're the ones that would be cooler and would be less appropriate. So I think the other important element in geothermal is the engineering piece. So just finding the hot rocks and producing the hot water is only half the story. You've also got to produce the electricity. Technologies for doing that are changing. So I talked about organic Rankine cycle. That's one of the latest technologies. But one of the interesting ones that's coming out now, so from the material sciences, is what's called thermoelectric generators. You think of it a little bit like solar panels. So it's a without any moving parts. It's two materials that, when put next to each other, and one is heated and the other is cooled, the electrons flow across it, and you can produce electricity just like you would with a solar panel when the photons hit it. So it's a heat thing, but it's the same kind of principle.
So these would be things that happen in the surface once you have already built
right. So that's the other thing. That's the other part of what you have to study is the engineering piece of it. I think the other interesting element, we keep talking about making electricity with geothermal, but that's only one part of the story. It is probably the most profitable part of the story, probably the most useful part of the story. But once you have hot material at the surface and you've extracted all the electricity you can from it, it's also useful for other things. So you could generate heat for homes, district heating. You could put it into industrial processes where heat is required as a part of making plastic or, refining oil and gas or any of that kind of thing. You can also do things like heating greenhouses, so you can increase the food supply by making greenhouses work 24/7, that kind of thing, and throughout the winter. So I think that once you have a geothermal resource and you make electricity from it, all these secondary and tertiary things are very valuable, especially to the community, where these are you have excess heat that you've got. It's waste, essentially. But if you can use that waste to make the people so they don't have to buy electricity to heat their homes, or it improves their lifestyle because it's heating greenhouses. You have all these sort of secondary and tertiary effects that make geothermal more palatable to the community. It's actually a valuable thing to them rather than a burden, an environmental concern, all that kind of thing. So I think there's a lot of things that are attractive about geothermal as being. I think it should be among the big three of renewable resources rather than the big two, which is wind and solar.
How would you transport the heat? Is there a way to transport? I mean, if I want my house to be heated by this kind of energy, how do you move the heat?
Well, heat isn't a challenging thing to move. One way to do is of course convert it to electricity and then convert it to heat, in a home, that kind of thing. But one of the nice things about geothermal, if you could have it broadly spread, imagine a microgrid, so a neighborhood being heated, having electricity being generated on site for all 300 homes in the neighborhood, but then the excess heat being used to heat those homes, heat and cool those homes, etc. So you think of geothermal as a distributed power source rather than as a centralized power source. When you think of, a power plant, a nuclear power plant or whatever, you think of this centralized source, and you need transmission wires and then distribution wires. But you could maybe change the paradigm entirely so that every neighborhood has their own power source for electricity, but also heat. And then you could also think of factories like a smelter or something like that, using the electricity to run their factory, but also using their heat to do whatever else they need in their industrial process. So it's an interesting thing where it's a little bit like the cell phones in Africa, right? Africa has basically bypassed the concept of landlines. So they went straight to cell phones, and so they don't have the distribution systems that we do. They don't need it. They jump past it. So that's a paradigm shift for the phone service. I'm thinking that geothermal could be a paradigm shift for energy service.
Is this already, does it exist in any part of the world, maybe in Iceland? Do they already have this kind of micro distribution of the heat?
They do, and there's another form of geothermal we're probably disrespecting, which is what's called ground loop or shallow geothermal, where you essentially put pipes on the surface, but no more than a couple of meters down, where the temperatures are rather stable and consistent and cooler than, at the surface. And there are a lot of homes now. I mean, I just drove by a truck driving over here that said, install geothermal at your home. So you're even doing it here in Houston.
Okay, so tell us more about this. How do you call it? What is the...
It's called ground loop or ground source geothermal. And you have to have enough space to do it. You couldn't do it with a very small garden kind of space, but as long as you have enough space, and some homes in Houston do have enough space, then you bury these pipes that allow you to circulate a working fluid. Most cases it's like Freon or one of these kinds of things. And it can either heat or cool your house depending on what time of year it is, because it's cooler than the surface in the summer and warmer than the surface in the winter. And so it can exchange heat that way. And so that's another form of geothermal, but it's a very localized thing. It's on a per home basis kind of thing.
But this is really potentially doable in every part of the world.
It is. Well, yeah. I mean, you have to have. You can't be sitting on bedrock, right? If you that kind of thing, because that would make it impossible to dig the trenches, But yeah, as long as you have enough 2 or 3 meters of sediments, then you could bury it almost anywhere in the world. That's right. And
this is also something that we don't hear about.
Surprisingly, yeah. I was very surprised to see the truck driving here, that it's something that's offered in Houston. But I have a friend who has it in the UK. He's had it for 10 or 20 years. So it's one of those things that, you only hear uncommonly. Because we, at least in the Western world, we have really good distribution systems, and we can get our power relatively cheaply from the grid, and we have our home heating systems, and it's just not that much of a requirement. But as we put more and more pressure on the environment, and we get more and more worried about that power that we're just getting from the grid and heating our homes with, it's coming from a coal-fired nuclear plant or a nuclear plant, and you're worried about the environmental impact, then we got to start looking at those alternatives, and they include things like ground loop geothermal or large-scale geothermal, like I've been talking about.
I have a very important question because we place the geothermal into the renewables sources of energy. Mm-hmm. And I'm wondering if it is really renewable, in the sense that once you, we say it's renewable because you can absorb the heat, and then the heat comes back. And so it renews itself, like the sun. It comes, you take the energy from the sun comes back, as well as the wind or the water.
The next day, yeah.
Yeah, but what about the heat in the rocks? Does it come back very quickly when we extract it fast?
Right. So that, I would say, is probably the top 2 or 3 problems with geothermal is the heat, what we call heat replacement. So you extract heat, bring it to the surface, and use it. But if you're not replacing it in the subsurface, it's going to get cold as you take more and more heat out.
Is nothing else than the analogy of the oil reservoir. When you pump up all the oil, then the reservoir remains without oil, so it's not renewable.
Right, but if you wait a couple of million years, that it is actually renewable. That oil will flow and refill that reservoir.
Exactly. We have to say that we use the word renewable from an anthropocentric point of view.
I think you're right. Now,
so what is the time of renovation of the heat in the crust?
It depends on the nature of the heat replacement. So if you think of in the closed loop example, if you just think of a pipe sitting in granite, the heat that you take away from the rock in the rock is being replaced by conduction. You remember from the old days of physics, there's different ways to move heat. One is conduction. Conduction is a very slow process. And so conduction, if you're relying upon the heat replacement in your reservoir by conduction, it's going to get cold too fast. And again, it's not going to be economic. You're talking about 5 or 10 years before you've reduced the heat so quickly and so much that it's just not replacing. So what you need to find in the subsurface is a place where you can get some other way of replacing the heat. In particular, think of convection. Convection is, remember, fluids moving around and moving your heat, right? The hot water rises, the cold water settles, that kind of thing. So if you took a pipe now and put it in a reservoir that had fluid in it, as you extracted the heat from the fluid nearest the pipe, it would sink and be replaced by more hot fluids. And that happens on the human timescale. That happens, conduction happens quickly enough that you can convection, I'm sorry, you're right. Convection happens quickly enough that you could have it, think of it as more renewable. On an anthropocentric, you know the word I'm looking for.
Anthropocentric.
Yeah, thank you. Timescale, that a reservoir could last 30, 40, 50 years before you suck all the heat out of it using the convection system.
I see. So still, the life span of a geothermal reservoir would be tens of years, not more than that.
We don't know yet. It turns out that we've done a lot of modeling on it, and yes, that seems 30, 40, 50 years seems to be a good time frame, but that's the lifetime of a nuclear reactor,
that is the lifetime of a reservoir.
Or of an oil and gas reservoir.
Yeah,
exactly.
So why do we place it into the renewables?
Because we can go somewhere else and do the same thing.
Or quickly. Just wait. Well, yeah, we go back to the time
frame. Yeah.
No, because we can go to other places also for oil and gas, but it's not renewable.
Yeah. Well, I think the renewable comes from the long-term view that there's a finite amount of oil and gas in the world, and eventually it'll be gone. At least on a shorter time frame, then there will be heat coming from the core and the crust of the Earth. That's not going to wear out anywhere near as short a time frame as oil and gas. So, the sun's going to burn out too, right? I mean, so
we go now into first semantics and now philosophy, which certainly has to hug the concepts of industry and energy and society, and I'm really glad that we are talking about this as well. Are there any topics that you want to mention about the geothermal energy that we didn't mention yet?
I think the interesting aspects of this relate to also in the oil and gas world, where we think about ownership of the subsurface. So before we ever drill, or often before we even explore, we try to secure the subsurface rights, right? We take in an oil and gas lease, or we bid for offshore blocks. This is really about gaining the right to access resources in the subsurface. We have the same problem with heat resources. So you'd actually have to gain permission to get into the subsurface, just like you would with oil and gas. But what's interesting is, in a lot of places, land ownership, the landowners, for example, in a subdivision built by Kelty Homes or one of these big subdivision builders, they'll often sever the surface rights from the subsurface rights. So the people have the right to own the land at the surface, but the home builder retains the subsurface oil and gas rights, because they're betting that maybe someday oil and gas is going to be found and they're going to get rich. But what they're not doing is severing the heat rights. So here's where it could get interesting, where you get this distributed model where you have a neighborhood that wants to drill a geothermal well. They might have the rights to do that, where they wouldn't in the oil and gas world.
Who owns the heat?
Well, it's the same question of who owns the oil. In theory, it's the landowner.
But the heat is not a substance. It's
not. You're right. But it sort of falls in the same category, I think, and it's treated in the U.S. and around the world in the same way. It's a resource.
Oh, like love. Also, love is a resource.
I don't think you have to get a license. Do you have to get a license for love? I don't know about that. Leasing?
A license for a hit, man.
And some love gets severed, I know.
Yeah, well, then you see, we are touching also on the jurisprudence of probably a new field for lawyers.
Yeah. So I think some of the other interesting things here, maybe quote a little numbers for those people who are a little more number-oriented. In terms of the U.S. geothermal resource is considered to be around 100,000 megawatts. And about 70% of that has been untouched. It hasn't even been identified. About 30% of that has been identified but is untapped, and less than 2% is actually is considered in service. So that's a huge space, a lot of headroom, a lot of opportunity for the U.S. Another interesting number for those that are interested, the actual cost of electricity produced by geothermal is an interesting number if you compare it to all the others. So if you talk about coal, you talk about natural gas plants, you talk about nuclear plants, they're all over $100 per megawatt hour. Geothermal is about 50, less than 50. If you talk about offshore wind, it's 63. If you talk about, that's onshore wind. Offshore is 157. Solar is about 85. So this is, when you levelize it and take out all of the other variables, it is a really cheap way of producing electricity. And one of the reasons is that the utilization rate is high. So with wind and solar, think of solar, utilization rate of solar panels, well, you know it's dark half the day, right? On average. Your panels simply don't get used for half the day, and then as the sun comes up, it's only for 20 or 30% of the day that you're getting good production. So your utilization rate is low. So you invested a lot of money to buy all those panels or whatever. You're only using them really 30, 40% of the time. In fact, the number here is 24%. That's the capacity factor. That's the utilization. 24%. So 76% of the time, the panels are not. Your investment's not earning you any money. The wind, it's about 45%. So the wind's not blowing essentially more than half the time. And these things are sitting idle, so all your investment's not earning you anything. The number for coal plants is about 85%. For nuclear plants, it's 90% capacity factor, utilization. Geothermal, 91%. So that's the fact that your investment is earning you money 91% of the day is a huge, makes it much more valuable than an investment in something that only works 30% of the time.
So, Malcolm, with this overarching view on the geothermal systems, what do you think that is still needed to have the geothermal energy more available to everybody? If you had to sum up.
Yeah, I think the number one, or the top three things, is cost of drilling, cost of drilling, and cost of drilling. We've got to find ways.
It seems it's cost of drilling.
Yeah, it's cost of drilling. We've got to find ways to make holes faster and cheaper and deeper for geothermal to work. The next one is how to deal with predicting the geology. Because you can make all the holes you want, but if they intersect geology that's not favorable for what you're trying to do, then you wasted your money.
There's going to be a dry hole, a cold hole.
Cold hole or something like that, exactly. Up to 50% of geothermal wells drilled now are dry holes or cold holes, as you call them. And so the success factor is very low. So they're very expensive, and you're wasting your money half the time. So these drilling-related things, we've got to get past those first. And then I think we're going to start to see geothermal take off.
So we need geology and engineers to collaborate together.
Yeah.
Once again. Well, thank you very much, Malcolm. That was great. Thank you so much. This is a mini geology radio show from KPFT HD2 channel in beautiful Montrose headquarters. And this is Daniel Minizini, your inquisitive geologist, today here with our friend Malcolm Ross, adjunct professor at Rice University. And this is all for now. Thank you very much, Malcolm.
Thank you.